Completed chapter 5. I originally thought that it was going to take me 2 more videos to complete all this work, but it turned out that there were 2 sections with applications that I only did a few problems for. Then when it comes to the reading, I completed chapter 5 reading, so chapter 5 is done. And then I'm up to 1,040 different problems that I have attempted up to chapter 5. Then just to show the book, of course, finally I'm at the gates of chapter 6. Chapter 5, I did some additional problems from, I think it was section 5.3, but then it was really mostly a couple of application sections and the supplementary supplementary problems. So the first one was differential equations. I only did the basics. It had an example, and I worked on a couple of the problems that were the same as the example. Then moved on. Then in the case of Markov chains, which I think are very interesting, I also did the same thing. I did a few examples. So Markov chains are all about sequential products. So you have this P matrix and you keep multiplying it as the system evolves. So it's just a way for a system to evolve, and sometimes they reach equilibrium, sometimes they don't, and so there are conditions for them to stabilize. And that was that. And then of course the supplementary problems. Then for the work itself, so I continued, again, of course, with problems, eigenvalue problems, the latter part of section 5.2. And of course, various proofs that have to do with the diagonal product. So it's inverse P, A, P is equal to B. And so, for example, in the case of a power, you can keep multiplying them, and they all, because P is invertible, they all kind of crunch up and you still get your power. And that's where you get the diagonal matrix to the power is equal to P minus 1 A to the power P. So there were several proofs that were similar to that at the tail end of section 5.2. And I did not do well on the true and false. I might as well have flipped a coin and I would have gotten the similar score. That seems to be a trend in the latter part of chapter 5. Then the reading of chapter 3, section 5.3, which are all the complex numbers. This one also, the key is to be neat, so it helped me get a little neater. For example, here I forgot that this was the conjugate, and so I got it wrong. Otherwise, I did okay, but every now and then, and of course, I tasked myself with getting it right. Every now and then I would get a conjugation wrong, and but otherwise it was just the same as reals, but now having to try to be neat with conjugation of complex numbers. Eigenvalues, eigenvectors for the matrices when they have imaginary eigenvalues, or the matrix itself is imaginary, one or the other or both. Of course, always trying to make sure that I get the right complex conjugates. Have my little roaming table of cosines and sines, just so I don't have to calculate them by hand every single time. Yeah, another thing here, I got something wrong, and I realized that the theorem that is used to work on some of these problems is only based on the eigenvalue of the negative imaginary number. So if your eigenvalues are 2 plus or minus I, the theorem only works on 2 minus I. And so I kept trying to use the 2 plus I, the first one, and I kept getting something wrong till I realized, yes, the theorem is only working for the second eigenvalue. That's how it was written. So once I figured that out, then I started getting things right. Theorem 538 is only for lambda is equal to A minus BI. And then also in the C matrix, C is A minus B, BA. The B is just a number. It's not, if it's 2 plus or minus I, it's just 1. B is 1. So I kept getting confused with that. Minor error here. Then when it came to norms, there was an interesting proof where u dot v is equal to a quarter of four different norms: u plus v, u minus v, u plus iv, u minus iv. And I laid it out. I figured out how to do it, but I couldn't figure something out. And the missing link was that by one of these theorems, this theorem right here, 533, u dot the constant can be imaginary. U dot kv, when you take the constant out, you have to do a conjugate, and that's how you get your negative number in here for all the terms to cancel out except for u dot v, and that's how you figure out that it's a quarter. So I got that right. Yeah, that was interesting. Again, I got to the true and false. I should have just flipped a coin for those. They tend to be a little tricky. I like them. I still like them. But sometimes I'm like, do you mean for all cases or just this case? And sometimes I get confused with that. Then, of course, when it came to the application for differential equations, there's a specific way of doing it based on an example. I got it wrong the first time. Then I checked my notes and I realized the mistake that I was making. I was not multiplying by the p vector, by the p matrix. And so then I got it right on one for which I don't have an answer, but then I did one for which I have an answer. And the book multiplied one of the vectors by 2. I don't really know why, but I know that this is the correct vector. So I have a small discrepancy with the answer for that problem, but I did yet another one, and I got the drift of how to solve it, and I moved on. Likewise for the Markov chains. There's a very specific way of doing it. I got them right, and that was good enough for me. And then I moved on to the supplementary problems, in which I did very well. I didn't do the last 2 or 3, but yeah, I did well in I think all of them. I got the drift of the chapter from the supplementary problems. Always, of course, trying a 2x2 and a 3x3 when somebody gives you a theorem that's for any value, and then you'll understand what the method is. Of course, there's also these problems on the Cayley-Hamilton theorem, which is used in abstract algebra, and I'm gonna make a video about that theorem in the various books that I have. I made sure that I did all those problems and I got them all correct, the ones that they have answers for, and I'm pretty sure even the even ones I got them right, because I could see how to get to it by just trying out a 2x2 or a 3x3. Like for instance here, I just did the 2x2. Yeah, I did the 2x2, and I got that it was lambda to the n minus 1 times lambda minus the sum of the coefficients, these coefficients. And then I did the 3x3, and sure enough, I got the exact same thing. So I was like, all right, so that's the general rule, and it is correct. Yeah. And I screwed this one up, but can't get them all. Anyways, that was chapter 5.